right, welcome, ladies and gentlemen, to another episode of Randall Responds, where we tackle questions from supporters of Randall Carlson and Cosmographia. Thank you guys so much for supporting the show. We get tons of questions, and Randall and I have promised each other that we're going to get to all of them one day. But today we'll tackle at least one. And
at least one.
At least one. And this first one is from Sean O'Luck. And he says, given that the extreme weight of peak glacial load on the crust causes isostatic compression, how possible do you think it could be that the compression would press the subglacial crust far enough into the mantle to cause the lower portion of the glacier to melt, while the ice age surface weather kept the top part of the glacier fully frozen? Also, I imagine the isostatically depressed crust naturally wants to spring back up. At the same time, the weight of the glacial ice would continue to press downward. Under such conditions, I suspect the entrapped water between these two forces would be under ever-increasing pressure. The resulting subglacial flows and eventual outburst flood could potentially achieve erosive force much more significant than any typical flood.
Some interesting points that Sean O'Lake makes there. I think this is a close approximation. I think the isostatic depression over the center of the Laurentide ice sheet, which would have been roughly around Hudson Bay, the isostatic depression was on the order of a couple of thousand feet. I don't know. Let me see. Do you recall right offhand what the thermal gradient, geothermal gradient is as you go deep? Now, I'm going to guess it's going to be more an effect of pressure than it is actually intruding into the mantle enough to. Yeah. But there would be easily geothermal heat involved. Absolutely. And it's very interesting to think about. Yeah, it's very possible. I think that weight would generate subglacial geothermal heat. It just seems, I'm going to have to think through the process, but that just seems to make a lot of sense. And that would create basal meltwater. We know that tempered glaciers, which are dynamically moving, will generate the friction of the movement will generate subglacial water. So there would definitely be a fair amount of water accumulated at the base of a glacier like that. And I think there is evidence. I mean, we know that there's large lakes under Antarctica.
Right.
They are the last papers I read on that, though, I do seem to recall, though, that they were pretty much confined to bedrock basins. So they weren't actually being held in by the ice per se. If you remove the ice, there's still the lakes would still be there, which is one of the things I've wondered about the role of Lake Pend d'Oreille in the region where the putative ice dam of the Missoula floods would have been located, because that's an 1,100 foot deep lake. And we won't get into an elaborate discussion about that right now, but there was certainly, I believe, a tremendous amount of frictional erosion there, because that was the outlet point for the draining of the basin of so-called Lake Missoula, which one draining alone would pass 600 cubic miles of water through that landscape. And if you have multiple drainings, then it's 600 times whatever the total number of drainings would be. That's a lot of water.
Yeah.
So he goes on here, the resulting subglacial flows and eventual outburst flood could potentially achieve erosive force much more significant than any typical flood. And I think he's probably on to something there. I wouldn't necessarily say, though, that that's the explanation for the Missoula floods. I still think we're dealing with something on a scale that requires melting much faster, on a greater magnitude, probably orders of magnitude more than you would find from subglacial pressure melting or frictional melting.
Yeah, I was thinking he was talking about maybe Drumlin formation. It's like, but that's just what I was thinking.
Well, if John Shaw is correct, Drumlin formation does require subglacial flows.
Yeah.
Significant subglacial flows.
Right.
Now, I don't know if pressure melting, basal pressure melting, or frictional melting of the glaciers moving on the landscape is going to be enough to generate flows on that level. And that's been the main criticism of Shaw's work, is the volumes of water required.
Okay.
Um,
Okay. Geothermal gradient. I found it. Wikipedia says temperature rises about 25 to 30 degrees Celsius per kilometer, or 72 to 87 degrees Fahrenheit per mile.
How much?
72 to 87 degrees Fahrenheit per mile of depth.
So let's just say we're talking a half a mile, and we're talking about 36 degrees.
Yeah.
Roughly.
Which is enough to melt water, or melt ice.
Melt ice.
Yeah. Generally. Just depends on the surface. Yeah. Interesting.
Mm-hmm. Well, that's something to think about. Good question, Sean.
It is. Great question. Thank you very much, Sean. All right. Let me pull up the next one here. So yeah, I tried to find that geothermal gradient in feet, but it's like they give it per kilometer or per mile. So
okay, well, kilometer is 3,280 feet.
Yeah. Well, 25 to 30 degrees Celsius per kilometer.
Okay.
Or 72 to 87 degrees Fahrenheit per mile. Very interesting that it's 72 degrees Fahrenheit per mile. What the fuck is going on here?
Huh.
Should have rang the bell on that one.
Yeah. Okay.
But yeah, what are we talking about? The isostatic response to 2 miles of ice is going to be what? A couple of thousand feet? How far is down is it going to push the? Do they know?
Well, I mean, yeah, because you can look at shorelines around Hudson Bay.
Yeah.
That are above sea level, so that gives you an indication of a minimal amount of rising.
Right.
And I've seen, and I mean, I think they're like 1,500 feet above sea level, but that's probably less than minimal. I think I've seen estimations of a couple of thousand feet of total rise.
Yeah. Okay.
Because some of the rise would have even started when Hudson Bay was still icebound.
Sure. So it wouldn't have lines, yeah.
Right.
Yeah, so if you could just roughly say it was a half a mile.
Yeah.
Yeah.
Roughly half a mile.
Yeah, then you would be 36 degrees Fahrenheit temperature rise. But I just don't know if that would translate all the way to the surface. I mean, does that count? I don't know. It's weird.
I don't know.
Because this is about digging down into the rock or whatever, right?
Yeah. Well,
but really? Like,
it's not digging into the rock. It's literally just like, sitting on a chair. You're not digging into the cushion. You're just depressing the cushion.
I'm talking about the geothermal gradient. Like, that's about going down into the crust, right?
Yes. Yeah. That's right.
Yeah.
So this is different. I mean, because now the crust itself, the surface, I mean, you're talking about the geothermal gradient, you're going below the surface.
Right. That's what I meant.
And now the surface is what's actually being
pushed. Yeah. Right. Yeah. Interesting. Okay. Let's tackle these two